Figuring out the shape of a molecule or a bond angle is a very common exam question, and it always starts with a dot and cross diagram. And this is a very common exam trick where they ask you to figure out the shape of a molecule or bond angle, but not to draw the dot and cross first. So people jump straight in and make silly mistakes. So here we go, dot and cross for methane is our first example. Once I've drawn the dot and cross, I can see straight away that I have got 4 pairs of electrons around the central carbon atom. And each of those pairs of electron essentially constitutes a region of electron density. And this is what we need to determine how many of these we have around our central atom before deciding on both the shape and the bond angle. So if I have to redraw methane, just using sticks, for bonds, it might look as though my bond angle should be 90 degrees, but we need to remember that molecules operate in 3D space, so we have to learn to think in 3-dimensional space. When we look at methane in 3-dimensional space, we can see that if those electrons, if those bonding pairs of electrons, and we can see here that that's what's represented on the diagram, electrons are all negatively charged. So if these pairs of electrons move to minimise repulsion between them in 3D space, we end up with a bond angle of 109.5 degrees. And this is common for all molecules where we've got 4 bonding pairs of electrons around a central atom. Once we can think in 3D, we have to be able to draw in 3D. So how do I represent that in terms of an exam question? Well, sometimes they ask you to draw it in terms of dashes and wedges. A wedge indicates a bond that's coming out of the plane towards me. A line indicates a bond that's in the plane, and a dash indicates a bond that's going back behind. So what I've drawn here is my representation of the molecule that we have in the illustration here. When answering exam questions to do with shapes of molecules and bond angles, language is absolutely key. So we need to mention how many regions of electron density we have, whether they are made up of bonded pairs of electrons or lone pairs. I'm going to come on to that one next. And that these regions of electron density are moving as far apart as possible to minimise repulsion. My next example is ammonia, NH3. If I were to draw it simply as sticks in 2D, it might look as though the bond angle is 120 degrees. However, that is in fact wrong. We need to go back to our dot and cross, always the dot and cross. Nitrogen has got 5 electrons in its outer shell, it has a lone pair, and then it uses 3 to form bonds with hydrogen. This means that round the central nitrogen atom, I actually have 4 areas or regions of electron density composed of 3 bonding pairs and a lone pairs. So this is going to form exactly the same structure essentially as methane, the tetrahedron, except that one of my bonds is a lone pair, so it looks as though it's missing. Hence we end up with this pyramid shape here. So in terms of drawing that, we've got the nitrogen, I've got 1 hydrogen coming out, 1 in the plane, 1 going back. And sometimes you see the lone pair drawn like so, and where it looks much more like a tetrahedron. So this particular shape is known as pyramidal or triangular pyramid. The language in chemistry isn't completely tied down, so you need to check with your exam syllabus and your textbook to find out exactly what you should call each of the shapes of these molecules. Bond angle. Well, the bond angle here is going to be round about 107 degrees. And the reason for that is that this lone pair of electrons because it's not a bonded pair, it's not shared between two atoms, it's pulled closer into the nitrogen nucleus, which means it repels the bonded pairs of electrons more strongly. We get more repulsion, it pushes the bonds together, so instead of a bond angle of 109.5, it's 107. The general rule is that for every lone pair of electrons you have, it reduces the bond angle by roughly 2.5 degrees. Following on exactly the same basis, let's have a look at water. Water takes the shape of nonlinear or bent or V-shaped. Once again, please check with your exam board as to which of those names you should be calling it, although there's often some flexibility when you have a look at the marking schemes. If we draw a dot cross for water, oxygen's got 6 electrons in its outer shell. We're using 2 of them to form bonds with hydrogen, and then it has 2 lone pairs of electrons. So this is going to still have 4 areas or regions of electron density around the central oxygen atom, composed of 2 lone pairs and 2 bonded pairs. They're going to move to minimise repulsion between them, move as far apart as possible to minimise repulsion. And as a result of that, we end up with a bond angle of roughly 104.5, because we've got the 2 lone pairs repelling the bonded pairs more strongly. Hopefully you can also see that this is essentially a tetrahedron with 2 of its bonds that have been removed. The next shape that we need to know is linear. Linear is not actually as common as you might think for all the reasons I've just mentioned, mainly lone pairs. But if we look at carbon dioxide, carbon forms 2 double bonds with oxygen. That's a lone pair on that oxygen. 2 bonds there, oxygen. Now, around this central carbon atom, I have got 2 regions of electron density. The fact that they're double bonds rather than single bonds is completely irrelevant, because they're in the same 3-dimensional space. Because of that, we can see that the bond angle here around this carbon atom is going to be 180 degrees. So just to be clear, a region of electron density is just that. We are not limiting it to a certain number of electrons. Trigonal planar or planar is a reasonably unusual shape for a molecule. We see it with elements from group 3, so maybe boron trifluoride, for example, aluminium chloride, because when boron and aluminium form molecules, they do so with only 6 electrons in their outer shell. They don't have a full octet, and the bond angle is 120 degrees. The other place that we see a bond angle of 120 degrees is in an alkene. So if I were to take, for example, ethene, then hopefully we should be able to see straight away that around either of the carbon atoms I have got 1, 2, 3 areas of electron density. The fact that one of them is a double bond is not relevant. 3 regions of electron density, move to minimise repulsion, bond angle 120 degrees. Octahedral is, again, quite an unusual shape for a molecule. A classic example is SF6, where we've got a sulfur surrounded by 6 fluorine. Sulfur's in period 3, it's expanded its octet, so it's clearly got more than 8 electrons in its outer shell. And when we're looking at this in terms of drawing it, we have got 4 of the fluorine in the same plane. So these 4 here, if you look at the molecule, they're all in the same plane. You could imagine it perhaps if you held up a sheet of paper so that you could only see the edge. That's what we're looking at here. So I've got 2 fluorines going back in 3-dimensional space, 2 coming out towards me. And then if we were to put a spike through our piece of paper, that's where the second two fluorines are. So one above and one below the plane. The bond angle here, either between the fluorines in the plane or between those two, is 90 degrees. If I were to take my octahedron, so let's do that, take my octahedron and remove the two bonds that are above and below the plane of the other four, I end up with a molecule with a shape that is square planar. Once again, this is really quite an unusual molecule. We see very few examples of that. Some transition metal ligands, for example, this one here, the nickel cyanide complex. That forms because what we have is the nickel. Each of the cyanide ions is making a dative covalent bond to the nickel from the lone pair on the carbon, and then the whole complex has got a 2 negative charge. Bond angle here is 90 degrees. Another common example is that of the tetrafluorochloride ion, obviously. That is C, now where are we going? Cl F4 minus. So let's start with a dot and cross. Once again, in exams you're often given us a molecule or an ion that is unusual to you, so start with a dot and cross. I've got 4 fluorines. We know that fluorine just makes single bonds, so let's start with them. 1, 2, 3, 4. Chlorine has got 7 electrons in its outer shell. I'm going to change the colour here, it's going to get confusing. So we've used up 4, so it's got a lone pair of electrons, and then it's got a single electron. This is a negatively charged ion, so I know that it's picked up an electron from somewhere else, and then that whole ion there takes on that negative charge. So from that I can see that I have got 1, 2, 3, 4, 5, 6 areas of electron density, but 2 of them are lone pairs. So again, going back to my explanation, take the octahedron, remove the one above and below, and we end up with a square planar shape. So doing a dot and cross, even if the exam question doesn't ask you to, is absolutely key to getting these molecules right, these structures right. And as I said earlier, the bond angle between the bonds there is 90 degrees. The last shape I want to look at is trigonal bipyramid or bipyramidal. Hopefully you should be able to see that what we have here are 3 atoms that are in the same plane, and then one above and one below, so very similar to an octahedron. In this case, because of that, we're going to have 2 different bond angles. The bond angle between the upright and the plane is 90 degrees, but the bond angle between the atoms in the plane is 120 degrees. In terms of drawing that, what we'd want to see is we've got 1 bond coming out, PCl5 is my example. I've got 1 in the plane, 1 going back, 1 above, and 1 below. Occasionally you have a more complicated molecule to look at. Once again, if you're asked about a shape or a bond angle, it's always around a central atom. So read the question carefully to figure out which atom we're talking about. So if it would be this alkyl carbon here, then I can see that I've got 1, 2, 3, 4 areas of electron density around my carbon atom. It's going to be a tetrahedral shape. Similarly around the second carbon. But if I were asked around the oxygen, then once again I must remember to draw in my lone pairs or to do a simple dot cross for this end of the molecule. And I can see there I've got 4 regions of electron density. 2 of them are lone pairs, so the bond angle here would be 104.5. This one here would be 109.5. So it's very straightforward to pull it all together. Just stick to the basic principles. Dot and cross first. How many bonded pairs? How many lone pairs? Decide on a bond angle. And finally, I want to consider what happens when a molecule becomes an ion, or there's some sort of reaction that happens. Occasionally you're asked to explain the changes, if there are any, in bond angle. Again, always go back to your dot and cross. So, for example, water. We've seen that water is bent, V-shaped, non-linear. It has 2 lone pairs, 2 bonded pairs of electrons, and a bond angle of 104.5. However, if water reacts with a hydrogen ion to form H3O+, which is known as the oxonium ion or the hydronium ion, then we have a different situation. We have oxygen. Let's put our bonded pairs in there. It has got 1 lone pair of electrons, and it uses its second lone pair to make a dative covalent bond to the hydrogen ion, hence H3O+. This changes everything, because what I essentially now have is 3 bonded pairs of electrons and only 1 lone pair. The fact that it's a dative covalent bond, again, is irrelevant. Those electrons are now being used as a bond. So in which case, if I have got oxygen, hydrogen, 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 1 lone pair, it now becomes pyramidal. It now becomes what the shape that we saw with ammonia. My plus charge there. And the bond angle is going to be round about the 107 mark. These numbers are not exclusive, so often when you look at the mark schemes you can see that there's a range. It might say 106 to 108. Anything in that range would be fine. And finally, to reiterate, at A-level, language is absolutely key. I've taught A-level 23, 24 years now, and I can genuinely say that the difference between one grade and other could be, well, it's often not what the candidate knew, it was how well they wrote it. And shapes of molecules, intermolecular bonding, there are certain things where you can write perfect answers. You can learn the right way to write your answer and then learn it. And this is where mark schemes are key. Go back to your exam board, check out a few past papers, find some shapes of molecules questions, see what language is picking up the marks and use that to write your perfect answer. But what we should be looking for, how many regions of electron density do we have? And surrounding the central atom, whether it's carbon, nitrogen, oxygen. So I might say there are 4 regions of electron density surrounding my central carbon atom. That's my first marking point. Second marking point, are they bonded pairs of electrons or lone pairs? Say, bonded pairs or lone pairs. If it asks you to state the shape, state the shape. If it asks you to name the bond angle, put a value on the bond angle, do that. Tick this off in the question to make sure you've answered all the little bits. Sometimes it's not that clear. People rush through and they leave out easy marks. In terms of an explanation for your bond angle, usually this involves lone pairs, but essentially what we're saying is that our regions of electron density or our bonded pairs, our lone pairs, are moving, so they move as far apart as possible, apart even as possible, to minimize repulsion. Some exam boards allow you to say that the bonded pairs, lone pairs repel each other, but many do not. So once again, just be really clear what language you need. Check your mark schemes, write yourself a perfect answer. If we're talking about why the bond angle is getting smaller in terms of lone pairs, then you would want to mention the fact that we have got more repulsion because these lone pairs are pulled in closer to the nucleus than bonded pairs of electrons. If this has been helpful, then please check out Crunch Chemistry, where I've put together a worksheet of common exam questions and answers to help you with your studies. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.